Hey everyone, ready to dive into some physics?
Always up for that.
We've got a good one today too. We're hanging out with one of the greats, Richard Feynman.
The one and only.
Using his lectures on physics, we're tackling a principle you see every single day, conservation of momentum.
And don't worry, we're ditching the dry equations. We're going full-on Feynman today.
Exactly. Making it clear, engaging, even fun.
Oh, Feynman was the master of that. He knew intuition was key, not just formulas.
Absolutely. That's what makes his work so timeless. So where does Feynman take us on this deep dive?
He starts simple, deceptively so, Newton's third law. The whole equal and opposite reaction thing.
Right, from back in school. Seemed pretty straightforward.
Sure, but Feynman could find the hidden depths in anything. He wanted us to get it, not just memorize it.
Okay, now I'm intrigued. How do you bridge that gap?
Imagination, of course. Picture two identical objects connected, then boom, a small explosion separates them. What happens?
Moving apart at the same speed, opposite directions.
Just
Makes sense, right?
Exactly. Our intuition's a good starting point. Now, Feynman tweaks it. One object's copper, the other aluminum. Same mass, but different stuff.
So same mass, different materials, same speeds after the explosion.
You bet. And get this. That's how physicists actually define equal masses. It's not just what it's made of, but how it reacts to a force.
That's mind-blowing. So if they respond the same way to the same force,
Yeah.
their masses are equal. Universal language of physics.
Precisely. To show this, Feynman uses one of his favorite tools, the air trough.
Now, I gotta ask, the air trough caught my eye when I was prepping for this. Why is it so important for studying motion?
Well, before the air trough, physicists were always fighting friction. Objects don't just slide forever in the real world, right? Friction messes things up.
Makes sense. Hard to see the elegance of physics when friction's in the way.
Exactly. Air trough was revolutionary. Basically eliminates friction. Objects float on air, almost constant velocity.
Ah, like creating a mini frictionless world, almost like Galileo imagined.
Exactly. Feynman could do these beautifully controlled experiments, isolate the principles, and he didn't waste any time putting it to good use. He designed a series of increasingly complex experiments, each building on the last.
Okay, so Feynman's armed with his air trough, ready to unlock the mysteries of momentum. What kind of experiments did he cook up?
He began with our familiar setup. Two equal masses, initially at rest, separated by a controlled explosion, but then he stepped it up a notch. One stationary mass getting slammed into by an equal mass already in motion.
So like a perfectly controlled collision.
Precisely. But he didn't stop there. Feynman was all about pushing boundaries. He started tweaking the mass ratios 1 to 2, 1 to 3, you name it, all the while meticulously tracking velocities before and after each interaction, looking for patterns in the chaos.
Piecing it together one collision at a time, using that air trough to strip away the real-world messiness, revealing something fundamental. And I'm guessing he finds dot conservation of momentum.
Bingo! As he walks us through these experiments, a clear pattern pops out. The object's velocities. All over the place. But one thing stays constant. Total momentum.
Like, quick refresher, how's momentum defined again?
Pretty straightforward, actually. Mass times velocity. Think of it like an object's, how much impact it have.
Gotcha. So a big truck going slow could have the same momentum as a little bullet going super fast.
Yeah.
Balance between mass and velocity.
Exactly. And Feynman shows us this momentum, it doesn't just vanish no matter how objects interact.
Even when they stick together. That one always kind of bugged me. Where's the momentum go in that case?
That's where it gets cool. They stick together, yeah, but there's a transfer of momentum happening. The final object, it might be slower, but it's more massive, right? Total momentum stays the same.
Like it's conserved, redistributing itself within the system.
Yeah.
It doesn't just disappear.
Exactly. And this holds true even when things get more complex. What happens when objects bounce off each other instead of sticking?
Now we're talking those springy collisions.
Right. And that's where Feynman introduces elasticity.
Like a rubber band. The more elastic, the more it snaps back to its original shape.
Perfect analogy. In physics, a perfectly elastic collision means zero energy lost. Objects bounce off with the same energy they had before.
Right, but in the real world, things don't bounce forever. Some energy's always lost, isn't it?
Absolutely. Real-world collisions are almost never perfectly elastic. Some energy dissipates as heat, sound, even just denting the objects a bit.
Makes sense. So perfect elasticity isn't ideal, but it helps us understand that energy transfer.
Exactly. But let's zoom back out. We've got conservation of momentum, this idea that it doesn't just disappear, But Feynman takes it a step further, right? Why is this so important for us to understand?
You read my mind. What's the big deal with conservation of momentum? Why should we care?
Because, as Feynman points out, it lets us solve problems even if we don't know all the little details of what's going on.
Oh, that's handy. Got an example?
Absolutely. Picture rocket propulsion. We don't need to analyze every molecule of fuel burning, the exhaust shooting out, to get how a rocket gains momentum.
Oh, right. Because of conservation of momentum, we can figure out how fast that rocket goes based on what's ejected out the back. We can skip the messy details.
Exactly. Simplifies things tremendously. But, of course, no physics principle goes unchallenged forever, especially with someone like Einstein waiting in the wings.
Here's where things get really interesting. Einstein, relativity. What did that do to our understanding of momentum?
Einstein, as he tended to do, threw a bit of a curveball. He showed that mass, something we thought was constant, isn't. It actually increases with velocity, and it's really noticeable as you get closer to the speed of light.
Hold on. Mass increases with velocity. So faster something moves, the heavier it gets.
You got it. Mind-bending, but experimentally confirmed. And obviously, big implications for momentum. At normal speeds, the change is negligible. But at those relativistic speeds, close to the speed of light, huge deal.
So how do you even calculate momentum then? Does our simple equation just go out the window?
It gets a relativistic upgrade, still fundamentally mass and velocity, but we use what's called the relativistic mass. Takes that increase with speed into account. A way to reconcile those super high speeds with the fact that momentum is always conserved.
It's incredible how Einstein's work shifted our understanding of something as fundamental as mass. Shows how physics just keeps refining our view of the universe.
Absolutely. And speaking of refining our view, this whole mass changing with speed thing, it might have you wondering, if energy can be hidden, like heat in a hot object, can momentum be hidden too?
Now that you mention it, yeah, makes you wonder.
Right. Feynman tackles this head on. He says, hiding mechanical momentum, the mass times velocity kind, is tough. If it's got momentum, it's moving. And we tend to notice things that move.
Right. Can't exactly hide a moving train. So no stashing momentum away like some invisible treasure.
Not quite. But there are places it can be tucked away. And this is where things get really wild. Electromagnetic fields.
Okay, now we're talking. Those fields around magnets, electric charges, they can carry momentum.
They can. And to see why, we need another Einstein revolution. Interactions aren't instant. Forces between charges, they take a tiny bit of time to travel.
So a tiny delay, an information lag between when one charge moves and another one feels it.
You got it. And in that split second, we're talking fractions of a second here, our momentum equation seems off. It's like momentum has vanished. But that's where the electromagnetic field steps in. It's like it carries the momentum during that transition, keeping things balanced.
Whoa, so the field's like a temporary storage unit for momentum, makes sure everything adds up even with that tiny delay.
Exactly. But it's not just a mathematical trick. There are real consequences. Think about light. It's electromagnetic radiation, and guess what? It carries momentum. No mass in the traditional sense, but it can still exert force. That's how solar sails work. They get pushed by sunlight.
Mind-blowing. Something as intangible as light can push, all thanks to this hidden momentum in the fields. It makes you wonder what other kinds of momentum are out there, just waiting to be discovered.
It does. That's physics, isn't it? Just when you think you've got it, bam, new possibilities.
Yeah.
But through it all, one thing remains constant. Conservation of momentum.
Right. From everyday objects to the quantum world where particles act like waves, it still holds true.
Shows you how deep this principle runs. Fundamental to how the universe works, even when our classical intuition breaks down.
This deep dive has been amazing. From colliding objects to relativity, hidden momentum. Conservation of momentum's been our guide the whole way.
Really shows the beauty of physics, how a simple principle connects things that seem totally different.
I love it. Well, that wraps up our deep dive into conservation of momentum. But before we go, something to ponder.
What's that?
We've focused on momentum in the physical world, right? Objects, particles, fields. But what about things without mass in the traditional sense? Momentum of a wave crashing on the shore, the spread of ideas, even social movements. They might not have mass like we usually think about it, but there's a kind of momentum there, isn't there?
You're really making me think like there are deeper principles at play beyond what we can measure directly.
Exactly. Something to chew on. Maybe there's a whole hidden world of momentum out there working in ways we haven't even begun to imagine.
Yeah, that would be exciting.
Wouldn't it? That's all we've got for you today. Until next time, keep asking those big questions, and we'll see you on the next Deep Dive.